Welcome back to another HVAC-Engineering-Techie video. This video today is part 2 of my journey through the carbon puzzle for energy production. We're going to talk about energy production. What's the best way to generate electricity without having a large carbon footprint? So this is the technical part. Part 1, which you can see in another video, was about the carbon and all the stuff that goes into carbon for Earth. So I hope you enjoyed part 1. That was a long video. This would be a much shorter video, but this is a much more technically demanding video because it's going to talk about all the technical things about power production. So remember, please become a subscribing member by hitting the subscribe button. Give me a thumbs up. Share this video with your friends. They might be interested in learning a little bit more about carbon and about power plants. I have to admit, I started down this journey trying to figure out for myself as a mechanical guy what's real about this stuff, because I hear so much talk. This one, I kind of put the thing I hear about, let's just go renewable energy everywhere and stop burning fossil fuel at all. And basically, I think this video will enlighten you on how that's not possible. It's certainly not practical. It's certainly not possible either. And so I hope that this is a learning experience for you, and I hope you enjoy the video. Thanks. So basically, what started all of this was people made statements to me about, well, we should just build solar photovoltaic plants, large plants across the deserts, and that'll solve all our energy future needs, and we can just use sustainable power. Well, I know a lot about solar, so I thought about that. I said, but, something don't feel right to me about that. So I need to do some research. So I went online and tried to figure out what's the best power plant and what do they do, and I discovered the data is not actually out there. It is out there, but not in a form you can use. The problem is every power plant has different efficiencies, different costs, different lifetimes, different uptimes. So how do you compare that? And when I started comparing those, which I'm going to walk you through that process, all of a sudden things came out much differently than I believed. So I thought it was interesting, and I thought maybe you would like to know a little bit about that. So having been a part of this PV solar industry early on, I understood PV systems and their shortcomings. I mean, I have built solar-powered power plants. They were small, 125 kW, but still they were tracking collectors that made hot oil. The hot oil drove a steam turbine. The steam turbine made electricity, regular power plant. I've built many photovoltaic fields, and I've commissioned those fields. I've recommissioned them years later to see how they look after they've been installed for 10 or 20 years. And that was somewhat disillusioning to realize that solar collectors and especially inverters don't last very long. They're getting better, but they are also getting worse depending on the quality of the collector. I had a friend that shot some, we use infrared cameras to actually shoot a solar field to see which ones are active or not. If the solar panel's damaged or not on, it's not hot. And if it's actually absorbing photons, it's slightly warmer. You can tell that with the camera. And we shot a bunch of collectors on a parking garage at a university, and these had just been installed 3 years before. And we found about 20 to 30% of them damaged and not working. These were cheap collectors from China. I have also done some fields that I installed that were 20 years old that the collectors were fine, but every one of the inverters were dead. So, I mean, there are some challenges. So I tried to figure out how can we compare those with other plants and what challenges they have, because it turns out every type of energy has its own challenge. I had people say that solar PV and wind is the only clean energy we should drastically expand their use to solve the climate crisis. Well, I somewhat agreed with that because I built several fields, but something didn't feel quite right. And it's always that mandate for maximum participation that gets you. I think you can support climate, support wind, but saying that it all should be wind and solar is not possible. I could not find any studies actually comparing the different types of power plants and their efficiency and CO2 production. Using the Department of Energy data, I created a comparison of the different types of power plants, each normalized for size, uptime, and lifetimes. So this was the only way I could compare them. The only way you can compare one type of plant to another is to make sure they're the same size, the same uptime, the same lifetimes. So, if one collector or if one power plant is up 90% of the time and others up 24% of the time, how can you compare them? I mean, because now the one's up 24% has to be 3 times larger to make up for the size difference. And lifetimes, what if one power plant lasts for 100 years? What if the other only lasts 20 years? Well, 20 years, you're going to have to rebuild it every 20 years. That's a problem. That's something you have to consider. So I took all of these things into consideration while looking at power plants. And you can't ignore them because the realities are real. The results were definitely not what I expected. So here's a U.S. electrical generation by source. So here's the different sources. Here's coal. And this is actually 2024 right here, 2023. It's 1950 to 2023. And you see, we've done a fairly good job about reducing coal, but most of our energy has come from coal in the past. The second one is oil and others, which is miscellaneous. That's this little strip here. And we don't use much oil for power generation. Mainly it's done for standby generators, but we do use some for primary energy where we have a lot of it. Then we have renewables, and that's the green strip. Now, renewables includes hydroelectric, which is certainly a renewable power source. You can see we've had it for a long time. And now this includes solar and wind, so that's why it's grown larger. You realize that that's still a big part of it is hydroelectric. And the nuclear is the red stuff. And you can see we're still been standard for it for a while. And then gas. This is natural gas. You can see we're burning more gas than ever to make up for the deletion of coal. And renewables has picked up the slack from not burning more gas, actually. So renewables have done some good by reducing the amount of gas. I wish we'd have just reduced coal more, but we'll talk about that in a little bit. This is about 4,178 billion kilowatt hours. So that's a lot of power. Now, the one thing you got to be careful of when you go and look at all this data is they mix up their units like terrible. And boy, you have to be really careful you're looking at the right data, because some power data is in megawatt years, and some is in megawatt hours, and some is billion watts per year. I mean, to change a units on you got to be really careful, because these are big units. You don't have a feel for them. You have to watch that really careful. Of course, I've always had a trouble with fully understanding where the decimal place is. Comes from when I first started, we were using slide rules, of course, and it's really hard. If you got the decimal place wrong, it really screwed up the answer. It still does, but it's a little easier now with computers. Renewable power generation. So this is 1950 to 2023. This is hydroelectric. You can see it's been kind of baseline for here. This is biomass, and this is geothermal. This little light line on top of this other line is geothermal, and this is wind, and that's solar. So this is all renewable stuff. So you can see the wind is a very large chunk, and solar is much less. But there is a problem here, and we'll talk about that in just a little bit. This is U.S. by source. This is residential usage, commercial usage, and industrial usage. And of course, this doesn't include transportation, so it doesn't add up to the total, but it's still where the electrical energy we're using in 2023. Okay, so comparing power plant data. This is the power plant data I collected. Advanced nuclear, which is a modern nuclear design of a light water reactor, 2,000 megawatts of big plants, 50-year lifetime, 93 uptime. Now, what does a lifetime mean? It means that the containment structures are good for more than 50 years, but the generators are not. 50 years is about the lifetime of a generator, so you're going to have to refurbish a generator. You're going to have to refurbish some of the electrical control parts. Probably the actual reactor part is probably good for a lot longer than 50 years. But they have a 93% uptime, so these very rarely go down. And this go down time is mainly for recharging the fuel every couple of years. So that's advanced nuclear. Coal, carbon capture, 650 megawatt is the typical size. 40 years is its lifetime, 49% uptime. We don't have a lot of these, by the way. We have a lot of coal plants, but not many are carbon capture. A regular coal plant, again, is 650 megawatt, 40 years, 49% uptime. Gas, carbon capture, 400 megawatts, 30 years. Slightly less than a coal plant, and only because they're a little smaller normally. 400 megawatt, but they do have a 54% uptime, so their uptime is greater. Their downtime is basically maintenance on the plant and what they call is a refurbish. Every once in a while they come in and refurbish. Gas, 700 megawatts, 30 years, 54% uptime. Geothermal dual flash, which means that we flash the steam twice, and it's not related to the atmosphere. 41 megawatts, so they're really small. 30 years, 71% uptime. Hydroelectric, 2,700 megawatt, even bigger than nuclear. Now this is the average size. 100-year lifetimes, 37% uptime. Why is the uptime so low? Well, the lakes are low, they can't run water, so that's why they're dependent upon having enough water to run the turbines, and that's why their uptime is not as great as it should be. Concentrated solar, which is solar reflecting on a boiler, 150 megawatts, 30 years, 24% uptime. You can see the megawatts are not very large. I don't know if you've heard in the news, but just recently they announced closing the facilities in Barstow, California that were concentrated solar. As far as I know, they're the only concentrated solar in the U.S. And they were mainly done for research, but they don't think they've proven their practicality for cost. Solar PV, 25 megawatts, really small, 20 to 25 years, 24% uptime. Uptime, of course, is because when the sun don't shine, they can't make power. Now, you got to understand that solar PV has something that most people probably don't know, is that you only make power when the voltage gets high enough. So when the sun first comes up, you don't start making power. It has to wait until the threshold voltage is achieved, normally over 300 volts. So you may not see the first 2 hours of sun time, you may not get any power production. And the same at the evening. As soon as the sun starts going down and you get below 300 volts, it cuts off. So the actual time is much less. We basically have 16 hours. You have 12 hours and 12 hours, but it doesn't work that way. You normally have 8 to 10 hours of sun time, power production, and the rest is nighttime. You have no production. Uptime. Now, lifetime, both these are the Achilles heel of solar. What this means is that 25 years, you got to rebuild the whole thing. You got to replace all the collectors. You got to replace the inverters. That's problematic if you're trying to build your future on a solar power plant. You just have to continue to replace it. It's just not practical. It's not feasible. And that's why I only promote rooftop solar. I think rooftop solar is a good thing because the owner, the user owns it directly. He can pay for it. He gets the benefit of how he uses it. It doesn't have line loss. It doesn't have distribution losses. To me, it's a much better solution to use solar than for trying to put it on the grid. Wind generators, 100 megawatts. They're getting some bigger nowadays, 15 to 20 years, 34% uptime. And they're just now getting to the point that these generators are starting to wear down because they're wearing out. And you see a lot of pictures on the internet of a wind generator failing and the blades falling off and the generator catch fire. Well, and Germany learned this lesson the hard way. I don't know if you know, but Germany made a decision several years ago to stop all nuclear and to do everything with wind generation. And they built these huge wind generators. And right now, they're building coal plants because they realize now they cannot survive on wind energy. One, their power went up 3 times in cost, just killing everybody in the country. And they're starting to fail, so they got to build them all over again. So this is something that you'd think really smart people would have figured out. They did not, and they are actually in big trouble trying to figure out how to get more energy. And they don't have natural gas, but they do have coal, so they're going to burn coal. So this is not a good thing, but it's what's truth. So I normalized it for size, I normalized everything for lifetime, and I normalized everything for uptime. So I said I'm going to change the numbers. So as if everything was 1,000 megawatts, the lifetimes were all 100 years, and the uptimes were all the same. And I've normalized the data. So this is what I started with. This is the Department of Energy data, and this has the 10 different types of power plants. Now, the gray stuff here is what the cost and everything to refurbish a plant of that type. And then across the top, it has the lifetime, the uptime, the site size, how many kilowatt hours it was, And then it goes across all the other data, capital cost, generation CO2, how much CO2 it produces, operating cost, fluid operating costs, so fuel operating costs. Some of these have zero cost for fuel because they don't use fuel. They're renewable. And then this is the total annual operating cost, total cost per kilowatt hour. And these are all based upon a couple-year-old data, so some of them are much higher than that. And this is an average cost for the U.S. It's not, some areas the costs are low, some areas are really high. So there are, and if one thing to understand, it takes so much to build a plant, and it takes so much to operate it. So this is fixed O&M per kW per year, and this is fixed operating cost. And these are the fixed operating costs, and this is the variable operating costs, which are the fuels over here, and total annual operating costs. So even though a plant is renewable, it has an operating cost of 23.40, and that includes the cost of people, the cost of money to operate the plant, a lot of things that cost operating. Now here's the maximum CO2, normal CO2 at initial cost. So here's construction CO2, and we also have here some operating CO2, because that generates, even a photovoltaic plant generates CO2 for its operation. Well, how is that possible? Well, it employs people. People have to maintain it, people have to operate it, people have to clean it, people have to work on it, and all those things generate CO2. So there's nothing that's CO2 free. Everything has some CO2 associated with it with producing power. A whole bunch of references, all Department of Energy, and you can clip this out of there if you want to look at it yourself. Feel free to do it. So here's the lifetime, here's the uptime, and here's the size. So I actually normalize these three things for everything to be the same. And basically I use 100 year for lifetime. I took the log. I use the size to be 1,000 megawatts, and I use the uptime. I just normalize them for the same uptime. And I think the uptime is whichever one was the highest. I think it's nuclear at 93%. So I made them all the same. And to do that, we come up with data like this. So this data sheet here shows the different types of power plants across the top. This is wind, solar, concentrated solar, gas, CO2 capture gas, coal, CO2 capture coal, hydroelectric, geothermal, and nuclear. So it looks at all these types. It comes down with all this data. And so over here we're talking about having equal size. So here's where I equalize the size, everything to 1,000 megawatts. Equal uptime. So we did everything to 93%. And then equal lifetime, everything to 100 years. And I changed all the other inputs accordingly by an equal percentage to what they had to have to equalize these numbers. And this comes out to 100-year revenue, 100-year operating cost, and 100-year profit. And this profit was all based all the same. For this, we assumed that everyone had the same sale price for power, and then whatever their cost was against that, and then their profit was taken back. Now, some people say, well, we don't care about profit for wind and solar, but we do, because there's no process here where people are going to operate power plants for no profit. So there has to be some profit incentive. Doesn't have to be a lot, but it has to be some. So you can't say that monetary advantage doesn't matter. It does matter. It's a practical matter. 100-year CO2 metric tons. So how many tons does each one of these deals produce? And here's how I concentrated all that data into just a few lists, and I ranked them between best to worst. And this is EAC ratings. EAC ratings are equivalent annual cost. And this is a mathematical calculation. It's the annual cost of owning, operating, and maintaining an asset over 100-year lifetime. So basically, I mean, these may not be intuitive. They weren't intuitive for me, but basically gas has the best because it's the lowest cost, it's the lowest operating cost, and over the 100-year asset, it's the most productive. So it's gas with CO2 capture, hydroelectric, wind, advanced nuclear, coal, geothermal flash, concentrated solar, cold CO2 capture, and solar PV. For EAC, solar PV is the worst, and that's because its lifetimes and uptimes are so small. So basically, this is not what the world out there is saying. Let's build solar and just forget about everything else. Won't work. It cannot, because you have to keep renewing the power plant every 25 years. So you're going to just keep spending money and money and money and money and money, and that is not going to work. You just can't do that. This has to be practical. The second one is profit rating. So again, gas is number one. You have to buy the fuel, but you can sell it. The plant is so cheap that you make more money than the others. Hydroelectric is next. Gas, CO2 capture, geothermal flash, concentrated solar, coal, advanced nuclear coal, wind. Solar PV is last again. And it's the problem with having to keep generating cash to renew this asset. And that's a big problem. Total CO2 rating. Now, this is where everything should shine. And this surprised me. The best one is actually hydroelectric. If you want to generate the least CO2 of anything for its entire operating life, hydroelectric is the answer. And so what have we been doing? We've been saying we got to shut these down because of the fish. Well, maybe you can figure out how to make those fish survive, but we need to keep the hydroelectric. We really need to keep the hydroelectric because it's the best we got. Advanced nuclear, that's next. Concentrated solar, wind, gas, CO2 capture, solar PV, geothermal flash, coal, CO2 capture, and gas, and coal is absolutely the worst. You can see the best is one, which is hydroelectric, and coal is 44.5 times worse than hydroelectric. Coal, solar PV is about 5.6, and coal is a lot worse than that. So coal does not, in my opinion, coal has no shiny advantages, except we have a whole bunch of it. But as far as cost, as far as profitability, as far as CO2, it's the worst. And initial cost. Again, so initial cost, gas is cheapest. CO2 capture, wind, advanced nuclear, coal, hydroelectric, geothermal flash, coal, CO2 capture, concentrated solar, and solar PV. So again, solar PV is absolutely the worst for cost, and it's all about the short lifetime. If you can make solar last 100 years, it would perform much better than it does today because it just doesn't last. You say, well, why doesn't it last? Well, how many computers are you working on that are 100 years old? Well, none, of course, because they weren't around. But how many computers do you have that are 10 years old? None, I'll bet. Not a one. And the reason is because it's advances and changes. You want the better thing. Well, in solar PV, the inverters are electronic devices, power electronic devices, which is even worse, and they don't last very long. 10 years is a long time for an inverter. 20 years, I don't know if that's going to work or not. So I think you have to count on a solar PV of actually being refurbished every 10 years instead of may last 25 years. Now, one good rule of thumb you can realize right away, what is their warranties? You realize the warranties originally were 10 years, and they went to 17 years, they went to 20 years, and some are still at 20 years, and some have pushed to 25. Well, they're not going to last past that because they're hedging their bet at 10 or 20 years. So this is a problem. Data results of normalization factors. So here's the uptime rating, which is advanced nuclear is 1 because it was the 93%. Geothermal, gas capture, coal capture, hydroelectric, wind, concentrated solar, and PV solar. So advanced nuclear is up all the time, and solar PV is 3.8 times worse than that because it's not up that often. And so, these are the difference for uptime and then lifetimes. And then lifetimes, you can see hydroelectric has the best lifetime of 100 years. Advanced nuclear is about 50 years. Coal is less. Coal capture, geothermal flash, gas CO2 capture, concentrated solar PV, and wind. So wind is the one with the worst lifetime because it's a big mechanical machine up there, and it is not going to last 100 years. There's no way. Number one, the wings and everything are made out of fiberglass, and fiberglass exposed to the environment doesn't last very long. So wind generators unfortunately have the least lifetime. So basically, with uptime and lifetime is cut the main renewables out of the picture, which is something you would think the world had figured out, but it has not. The other thing, which I didn't mention here, which we'll get to later, is to actually use wind and photovoltaics as grid-tied power plants, you need to have storage. And storage is not well done yet. It's so expensive. It's almost 3 times more expensive than the solar or the wind itself to do the battery storage for it. So this is another problem. These renewables are not well baked yet, and we should not be dumping all our eggs in that basket until it is. It results from low CO2. So we just look at CO2. Here we see hydroelectric is the best. And what this is combining A, B, and C, which is the, if you go back and look at what A, B, and C is. A is EAC, B is profit, C is CO2, and D is cost. So here you can see in these, we're looking at hydroelectric is the best of A, B, C, which is carbon. 5, so next is gas, advanced nuclear, wind, concentrated solar, thermal flash, geothermal, solar PV, coal, CO2 capture, gas, and coal. So if you're just going to look at those 3 things, which is the EAC and C, then you're going to come out with hydroelectric on top and coal absolutely last. So that's one thing. So you're looking at profit and CO2. It's not a bad way to rate them. Or you can look at this one, which is EAC, profit, and cost, which leaves CO2 out of the picture. Then also you see gas is best, followed by, and coal is in the middle, and solar PV is the worst. So, if you're not considering carbon, renewables are not in the picture at all. So we need to be cognizant of that. Now, wind is a little bit because it just has EAC and profit, but it doesn't have, and the cost includes the replacement. So wind has a D, but it still doesn't include the storage. So remember that hydroelectric, we have few sites. Advanced nuclear takes a long time to plan and build. Wind is community impacts. They're having some pushback there. And concentrated solar needs clear sky. So out of this, basically, if you're trying to do the best you can on cost and feasibility and CO2 with capture is probably the best bet. Over here, for just profit, then these are the only options. None of these are actually options. Their numbers are way too high. And basically, CO2 gas capture is the only one that does both. Now, CO2 capture is somewhat of a problematic issue, but if we had capture down good, this would be what these numbers all push out. That's as far as being practical and possible to do and practical to do, and will help us lower our carbon footprint to a reasonable amount. So what we're doing by depending on solar PV and wind, we're ignoring the embedded carbon in the devices themselves and pretending that those produce no CO2 and they will solve our problems. They do not. So these are not good alternatives for us. Best overall pick is gas with CO2 capture. This is one that took me a while to develop. Okay, this is one that I had to think through a while. Is some of my engineering colleagues said, well, this is build solar. We got lots of land. We can put the solar aside. Well, how much land does it take? And they said, not very much. And it didn't feel right to me, so I think I better calculate this. Well, that turned out to be harder than I thought. Some people say it's simple, but not for me. So basically, here's the electrical energy production. Here's the coal, the different types. And it comes to 4.178. This is actually a billion megawatt hours. A lot of power. Another one of those unit deals you got to be careful of. Then over here, I took it and said, okay, we know how much each type is. So let's take the total and let's subtract out all renewables: hydroelectric, geothermal, wind, and solar. And we come up with 3.3 million watt hours per year. Okay, again, we changed now from billion to million watt hours. And so we know this is how much we need to increase to get rid of all the other standard power and just use renewables. So if we want to make wind and solar do 3.3 million watt hours a year, we'd have to do this many kW. And let's see, that's million. That's million. So it's 3.3 trillion kilowatt hours a year to be able to do that. And that would require, so the kilowatt hours per day per square foot is that on a solar collector. And it means that a solar collector, a typical solar collector, this is per square foot per year, is about 37 watts, 37 kilowatt hours a year. So basically that's what we have to work with. So to figure that backwards, it's going to take 89, no, I'm trying to read these numbers. So this required square foot of solar would be 89,253,392,948 square feet. We're going to need a lot of square feet. Well, that works out to about 2,048,000 acres of solar, flat land that we can use that on. Acres of storage support, we're going to need about another 1 million acres for support, roads to get there, support structures, and storage. We're going to need about that much. So we're going to need a total of 3 million acres, which really is not that much land. About 4,800 square miles. And the cost of PV per kW is about $26.71. This is an average. I realize they all can change. And the cost of storage right now is about $42.93 for that same kW. The total cost is about $6,964 per kW, and that doesn't include land. That's just the facilities. So that would be about kW a day collected in storage, so about 9 billion 126 million kilowatt hours a day. So the total cost, including that, is $63 trillion. 63.553. $3 trillion that you need to spend every 25 years. The U.S., the most prosperous nation on earth, cannot afford this, and neither can anyone else. So 82 billion square foot of solar required includes increased size of uptime, 3 million acres, flat land, 4,800 miles, 63 trillion every 25 years. Solar and wind will not be able to solve our energy needs due to uptime and lifetimes. Now, I would have thought smart people would have figured this out before me, but evidently not, because they're running down the road as quick as they can into oblivion without figuring this out. So anyway, that's what the things I calculated out that surprised me. What would change these projections? So if major reduction in the number of people, so if we lose half the people on Earth, the CO2 will change. Major reduction in use of electricity. That's not going to happen. We're trying to figure out more and more ways to use it, not less and less ways to use it. Major invention and development of carbon capture technologies. If that makes a big difference, then they could change it. Final commercialization of fusion power. So if we get more fusion power, that may solve this problem. What will make things worse? Major growth in population. Quickly converting to electrification. Mandating that every vehicle become electric on the roads. We don't have the power infrastructure for it, and you will cause a disaster by doing so. Quickly converting to electric transportation by all kinds. To me, one of the things that's comical is let's build electric diesel trucks. That's crazy. Do you know how much weight a diesel truck has and how many miles they travel a year? A battery production just not going to work for that yet. That's not in the books. Fast growth of AI. This caught us by surprise. AI now is growing at a rate that could actually swamp our entire electrical infrastructure within the next 3 or 4 years. I have some numbers on this later in part 3, but this is a shocking thing. Fast growth of blockchain or Bitcoin. Bitcoin, remember, is based solely on calculations, which takes data centers, which takes power. And basically, so what we're doing, we're squandering our electrical heritage so somebody can make a profit. To me, that's a bad idea. I think Bitcoin and blockchain may be a great intellectual problem, but should not be allowed because it's going to hurt us. And it doesn't mean just because you can go lose money at Bitcoin, it means your cost will raise because they're out there using our energy. Major growth in manufacturing. Expansion of war across the globe. War causes a lot more carbon, so that hopefully doesn't happen. So we covered part 1, we covered part 2, we've covered what the party said. Now part 3 covers what should be concentrating on to improve carbon footprint while improving our world and the lives of its people. So we'll go into a lot of these predictions about future growth and what we need to do to meet that future growth. So I hope it's helpful. I hope you enjoyed the video. Sorry about my voice. Gravelly, that's what age does to you. But I hope you've been able to understand. Thanks for watching the video. Remember to share. And that's it. So I appreciate you watching the video. Be sure to watch part 3. Share with your friends and neighbors. Catch you on the next one. Thank you.